Hello, in this video we're going to look at the ideal gas law and how it describes the properties of an ideal gas. We will see how the macroscopic variables of the ideal gas law appear from the microscopic interaction of particles. So the first obvious question is, what is an ideal gas? On the left we have an ideal gas and on the right we have a real gas. Both of them are in the same volume, the same temperature. At first glance it doesn't look too different, but there are some subtle differences. An ideal gas is a set of non-interacting point particles. Here we show them as moving circles only for visualization. You can see that the particles do not interact with each other, they basically pass through each other. A real gas, on the other hand, consists of non-point particles, and so they occupy some of the space available and have both attractive and repulsive forces between them. Here we can see them bouncing off each other. If the gas molecules are complex, then they can have significant rotational energy or internal vibrations, which makes them behave differently from the ideal gas case. In both cases shown, these are closed systems, that is to say energy does not enter or leave the system, as the walls are perfectly rigid and hence the particles bounce off them. As you can imagine, the ideal gas law does not describe almost any liquid. And so what is the ideal gas law? So here it is. It describes how P, V, N, R and T are related. So P is the pressure, and it's the pressure that the particles exert on each other and on the walls of the container. V is the volume in which contains the particles, so the volume of the container. N is the number of moles, which is just a fancy way of saying it is the number of molecules of particles of gas. One lot of N contains over 602,214 billion particles, so 1 mole is a lot of particles. R is a constant known as the universal gas constant, and T is the temperature, which is related to the average kinetic energy of all the particles. What is good to note is that if a real gas is sufficiently sparse and contains only simple small molecules, then it obeys the ideal gas law. In fact, at room temperature and up to tens of bars of pressure, the ideal gas law describes a real gas very well. As such, it is an important equation for scientists. Now, just looking at the equation, it is interesting to see that there is no obvious mass term. So, at the same temperature, it doesn't matter if the gas is monatomic helium, a light molecule, or diatomic oxygen, a considerably heavier molecule, only the number of molecules matters, which is very interesting. So let's actually explore what P, V and T are, and what this equation tells us. So what is pressure? Well, we can rearrange the ideal gas equation for pressure. And we can see that pressure arises from having n particles at a particular temperature placed inside a volume V. And here we have a basic particles in a box simulation of an ideal gas, as we previously saw. However, this time on the bottom we're plotting pressure versus time. So the particles behave as an ideal gas, not interacting with each other, but when colliding against the wall, they are treated as hard spheres and collide elastically. We know from physics that pressure is the force exerted per unit area, which in our case is the force exerted per unit line length. So a big line with the same force means smaller pressure, and a small line with the same force means a bigger pressure. We also know that force is the change in momentum over time. So every time a particle hits the line, it exchanges momentum. The particle bounces off the line, experiencing a force. Newton's third law tells us that the particle experiences a force, then the line experiences an equal but opposite force. And that's what the plot on the bottom is showing. The pressure exerted on the red line. Each dot is a particle applying a momentary force on the line. Faster particles give a bigger force, or straighter collisions give a bigger force. The solid line is the time averaged value of this pressure. We can see that on such a small scale with perfectly elastic collisions and hard particles, the pressure is not completely smooth. This highlights one of the fundamental differences between microscopic and macroscopic phenomena. On the molecular scale, pressure is not a constant value. In fact, pressure is a macroscopic phenomenon. This arises from taking the average of a large number of these microscopic events. And it also shows that pressure is derived from looking at the statistical mechanics of all these microscopic Newtonian mechanic events. Now, to explore what pressure is further, let's see what happens when we change some of the properties of the gas. So according to the equation, if we double the number of particles, the pressure should double. But why? When we increase the number of particles in the box, we can see that the average force a particle exerts on the box is unchanged. The particles on average have the same speed in both boxes. That is to say, they are at the same temperature. The difference here is the frequency of collisions. Since there are twice as many particles in the box, there are twice as many collisions with the line. This means the average value of force and hence pressure rises, which you can see from the bottom plot. Pressure on the right is approximately twice the pressure on the left, and this is due to the increased number of collisions, which you can see by there being approximately twice as many dots on the right as left, so twice as many individual collisions. Now let's take a look at temperature. So according to the equation, if we double the temperature of the particles, the pressure should double, but why? So temperature is related to the average of the square speed of each particle, and so to double the temperature, we have to multiply the speed by square root 2, which is about 1.41. We can see that because the particles on the right are moving faster on average, the force they exert on the line, and the frequency at which they collide with the line is increased. So that is to say, the particles exchange root 2 times more momentum with the line on average per collision, and they also collide root 2 times more frequently, resulting in a force twice as large and hence a pressure twice as large, which again we can see on the line on the bottom. Now let's see what happens when we change the volume. So according to the equation, if we halve the volume, the pressure should double. But why? So here, halving the volume is the same as halving the area of the box in 2 dimensions. So a smaller box means the particles collide more frequently. In this case, it's square root 2 times more frequently, as the distance a particle must travel has decreased by square root of 2. Additionally, the line is now square root of 2 times smaller. So square root 2 times more frequent with a line that is square root 2 shorter, again results in double the pressure. So this equation is indeed describing pressure very well. It's capturing the macroscopic state of all these microscopic events. So I hope this clearly shows what pressure is and where it comes from. We've seen how the ideal gas law, when written out in terms of pressure, shows the correct behaviours for changing N, T and V. We've seen how these quantities arise from very simple Newtonian mechanics of small particles. And so pressure is a macroscopic phenomena that arises from microscopic events. Now let's try to understand what we mean by volume. So we can rewrite this equation in terms of volume. But what does that mean? Isn't volume fixed? Well, the answer is a little more elegant. So here we have another particle in a box simulation as before, but this time we have a wall in the middle. This wall is free to move and experiences no drag, hence the wall becomes like a big long particle, able to take and give energy within the system, but never able to take energy out or give energy to the system. Go ahead and look at the simulation. We can see that we have on both sides an equal number of particles at the same temperature on both sides walls. That is to say, the average kinetic energy is the same. The pressure they exert on the line, on average, is also the same. So by looking at the bottom plot, which again is pressure versus time, the net pressure exerted on this moving line on average is 0, so the line stays in the middle. There is just as much pressure coming from the right as there is on the left. And although the line wobbles slightly on the microscopic scale, we see that it stays in equilibrium. Now what happens when we change the number of particles in one side of the box? The volume should change, right? We can see that as before, more particles at the same temperature results in more collisions with the line. This means there is more pressure on the right than the left hand side. This does not mean that the left hand side does not exert any pressure, however, it's just less. These collisions exchange momentum with the wall, causing it to move left. Once the wall moves left, further collisions on the right will further accelerate the wall, meaning it starts to move faster to the left. The particles on the left hand side of the wall act to slow the wall down, but are overcome by the pressure exerted on the right hand side. However, since the collisions on the right are reducing the average velocity of the particles on the right, as well as changing the distance the particle needs to travel to hit the wall, the frequency of collisions decreases. Likewise, on the left, the frequency increases as the distance becomes smaller and the particles begin to pick up extra speed from the oncoming wall. Eventually, the pressure on the left-hand side rises to counter the pressure on the right-hand side, and the wall begins to decelerate. However, since there is no friction on the wall, and the wall has momentum, the wall overshoots, causing the pressure on the left to increase above the pressure on the right. The result is a springy system where the wall actually oscillates from left to right, causing temperature, volume and pressure imbalance. And so by having a moving wall, we can see that the pressure has become a driving force for change. If there is a difference in pressure, volume and temperature will change in response to this pressure force acting on the volume. So volume can be thought of as the volume that is occupied by the particles under neutral conditions, so under equilibrium conditions in which there is no net driving force. And so on average, this line lives approximately to the left of the middle from where it started. Pressure on average drives it to be on the left. Now we can look at the same situation, but what happens when we have an uneven temperature? So the particles on the right are at a higher temperature than the particles on the left, despite having the same number. We get the same situation. The higher average velocity on the right results in more collisions with the line. This means there is more pressure on the right hand side than the left hand side on average. These collisions again exchange momentum with the wall, causing it to begin to move left. Now this wall is moving, further collisions on the right will further accelerate the wall, but slow down the average speed of the particles on the right. And again, since the wall is moving to the left, it imparts momentum on the particles to the left, increasing their temperature, so their average velocity, as well as decreasing the distance they need to travel to collide with the wall. And again, eventually the pressure on the left hand side rises to counter the pressure on the right hand side, and the wall begins to decelerate. And because the wall carries momentum, this system is springy, we get oscillations. But again, we see that the wall on average lives to the left hand side of the middle from where it started. And so again, by having a moving wall, we can see that pressure has become a driving force for change. The volume and temperature changed in response to the pressure imbalance, which was caused from the initial imbalance in temperature. Also note that the particles do not exchange temperature with each other, only the line. And so the line is allowing thermal conduction between the two parts. So what is temperature? Well, the temperature of a collection of particles can be found by calculating the following. And as I say, temperature is related to the average speed of the particle. What I actually should be saying is that temperature is related to the average square speed of the particle, or the average kinetic energy. And more interesting, it is proportional to the average kinetic energy of the particle. So the equation shows T equals 1/3 kb m times the average of the square speed. So kb is the Boltzmann constant, which is just a constant, m is the mass of each particle, and v squared is the average square particle speed. And so it's a macroscopic variable that describes a large number of particles. The individual particles themselves obey Newtonian mechanics, but a large enough number of them obey statistical mechanics. So T is a statistical phenomena. We can see that the mass does appear here in this equation, and so two different particles at the same thermal equilibrium may have different average square speeds, but on average cannot exchange kinetic energy. So a particle that's 4 times bigger on average would have 2 times less speed at thermal equilibrium, and this comes from the momentum exchange between the product of V and B. So remember, momentum is mv, so big V with small m, or small v with big M, result in the same kinetic energy. So that's why small molecules like hydrogen typically whiz around much faster than larger molecules such as xenon at the same temperature. And so let's see what we can learn from rearranging the ideal gas equation for temperature instead. So here we have another particle in a box simulation, but this time we have a wall, and this wall we are going to move. So we're applying a force to the wall, which moves the wall to the right. So I've coloured half of the particles red and half of the particles blue. They all share the same mass and temperature, hence the average square speed. As we move the wall to the right, we start to give the particles a small kick. So the particles bouncing off the wall moving towards them will bounce back at a speed greater than the speed that they hit the wall with. Both the red and blue particles get these little kicks, and hence their average speed increases. Hence, so does their average square speed, and hence temperature. Any small difference between the red and the blue line becomes more apparent. Blue started off slightly closer to the wall, and so gets more of a kick, meaning it achieves slightly higher temperature. And so we can see that compressing the particles by changing the volume of the system and imparting energy onto the system from the wall changes the temperature. The pressure increases until it becomes great enough to stop the wall from moving. Now what happens if you allow particle-particle interactions? So it's the same simulation as before, but now the particles can interact. And you can see that the particles now bounce off each other until thermal equilibrium is reached. They're still getting the little kick from the wall, so their overall temperature is increasing, but the individual particles themselves are free to exchange momentum with each other. You can see that there are random fluctuations due to these particle-particle interactions that result in the particles having a distribution of speeds, and likewise all particles themselves having a distribution of speed. So trying to follow any one particle, you will see that sometimes it's slow, sometimes it's fast, sometimes it sits in the middle. An individual particle speed cannot be determined, but its average speed can be, or its distribution of possible speeds. On such a small scale, picking out half of the particles and calculating the temperature will cause fluctuations, as you can see in the bottom right. This goes to show that the temperature is a macroscopic variable. It's caused by all these individual small collisions, or it's caused by the sum of all the individual kinetic energies of all these random moving particles. And so penultimate example. So here we have a situation with two coloured particles again. The particles in the middle have the same density as those on the outside. That is to say that n divided by v is the same. The volume the red particles are contained in divided by the number of particles is the same as the volume that the blue particles are contained in divided by the blue particles. Through particle-particle interaction, we're going to see that the red particles, which start off with a higher temperature, will achieve thermal equilibrium with the blue particles. So at first, the red particles are moving faster than the blue particles. After several cycles of collisions, we can now see that the blue particles and the red particles are moving with the same speed on average, so have the same kinetic energy on average. This is because they're allowed to collide and exchange energy with each other. And you can pick out any individual particle and you will see that the fastest moving particle may be a blue particle, even though the red particles were faster on average. It's all about averages. Temperature is a statistical phenomenon. It doesn't tell you anything about an individual particle, it only tells you the likelihood that an individual particle has a particular speed. And going back to the beginning, we can also see that the red particles spread out, so they become mixed with the blue particles. So because they're at a higher temperature within the same volume, with the same density, you can almost think of this as like a pressure. So having a higher pressure means that the red particles are likely to collide more frequently, which they indeed do, because they have more kinetic energy, they have more speed. However, by colliding they exchange some of the energy and hence their pressure decreases. Now it is kind of strange to think of pressure like this, which again highlights the difference between what pressure is at a macroscopic and microscopic scale, and whether you can really define pressure for such small scales. This does not mean that blue particles are always slower than red particles. On average, at the beginning this is true, but if you picked any one particle and follow it, you will see that its velocity and speed constantly changes through collisions. I have another video about this on my channel where I look into this and derive the distribution of speeds from these particle-particle interactions. And now, as a final example, let's see what happens when we separate the coloured particles. So on the left, we have blue particles, on the right, we have red particles. Both particles are at the same initial temperature and with the same volume, and so experience the same pressure. As we move the wall to the right, the blue particles begin to lose velocity and the red particles begin to gain velocity. So the wall moves into the red particles, causing them to gain velocity. The wall moves away from blue particles, taking some of that velocity away. The result is a system in which the blue particles have a lower temperature than the red particles, and the red particles gain a higher temperature than they initially did, showing the effect of both compression and expansion. And this wall is moving at a reasonable speed, and so the blue particles undergo dual expansion or close to it, which means the temperature actually hardly changes as the particles fill their new volume, so the wall moves relatively fast compared to the average kinetic energy of the particles. And the pressure on the left hand side decreases as the pressure on the right hand side increases. The pressure on the right hand side eventually becomes so great that it stops the wall moving. We can't apply any more force to move the wall. And so in all cases it was not possible to change one variable without changing the other. Since we are doing something to the system changes in response. There are various laws and equations that describe these thermodynamic processes so that you can work out the temperature, volume and pressure during these state changes. And so what have we learned from the ideal gas law? We've learned that pressure is a macroscopic result of particles hitting the walls of the container. That is to say, pressure is a driving force that causes the system to change. It can cause both the volume and temperature to change. Volume is the volume that n particles would occupy when in equilibrium with its container. That is to say, pressure and temperature equilibrium. If the container is fixed, then the volume is constant. And temperature is related to the average kinetic energy of all the particles. So if particles are allowed to interact, the temperature will evolve to reach equilibrium. Changing any one of these, pressure, volume, temperature, or even particle number, can drive a state change depending on whether the container can change or the particles can interact. So I hope you at home watching this found this interesting and informative. I think these little simulations are a great way to see how macroscopic quantities such as pressure and temperature arise from microscopic movement of particles. And so thank you for watching. Oh, and just one more note. I will be releasing a video like this, but looking at how diffusion arises from particle-particle interactions, so stay tuned for that. It's going to be exciting.